This next one's still a stoichiometry. This is a stoichiometry that just happens to deal with energy. This tells us our delta H, which we can kind of say heat, but it technically is enthalpy, is negative 1170. That means at the end it's going to release. For this reaction to occur, it's going to release 1,170 kilojoules. I'd put that over here. If it was positive 170, that would mean I'd have to add that, and I'd put it over on the left side. Because it's on this side, it is exothermic. Okay, so the first step, yeah, there was parts of it. I'm going to treat this like stoichiometry. Start with balanced reaction, check. Figure out, what do they want to know about? How many grams of ammonia gas? We need to remember that ammonia, NH3, not the first time we've seen that. That's going to be what we're asking about. They want to know about that. They're going to tell me, in this case, the given is the amount of energy. If we started with, if we ended up with 1170 kilojoules of energy, that would have meant we started with 4 moles of ammonia. We're only starting with 164 kilojoules of energy. So I need to figure out, like typical stoichiometry, how do I get from, if I'm only going to make 164, how much am I going to get? Well, I'm going to check the mole ratio. 4, which will go on top, moles, comes from 1170. So if I take 164 times 4 divided by 170, like we do for stoichiometry, I'm going to get 3.86 moles. 3.86. That doesn't seem to make sense. So let me just double check. 4 moles. I'm going to put that in the calculator again. Seems like that's not even close to 1170, but I'm getting close to 4. So clear 164 times 4 divided by 1170 equals 0.56. So sometimes just using like math in your head, you might be able to check the logic. 0.56. 0.56 moles. Why did it look suspicious? Because it was too close to 4. So that should have been close to 1170, but I was nowhere near there. I'm going to have 0.56 moles. That's not what they want to know. They want to know how many grams of that. 0.56 moles of NH3, that's ammonia. 1 mole of NH3 is a 14 plus 3 is 17 grams. I still have this into the calculator, times 17, approximately 9.5. 9.5 grams of NH3. On to the next one, some theoretical stuff, some model-y stuff. I might want my periodic table, which has a lot of good information up here about certain things. They're just asking. When I see this P1531, understand that this here is just P's, phosphorus's atomic number. Atomic number. I can verify that. Go find phosphorus. Yep, its atomic number is 15. Its atomic number is its number of protons. So when this is asking me that, let's see, how many protons equals 15. It's telling me it's neutrally charged. It doesn't have a positive, it doesn't have a negative, therefore its electrons are the exact same number. Does that say that up here? Yep. For a regular atom, unless they tell me it's an ion, the protons equal the electrons. So then, what about the other part? Well, the other thing is called the mass number. That's the protons plus the neutrons. So when I'm going to look at this 31 is called the mass number. And if there's 31 as the total protons and neutrons, and 15 of that is protons, 16 will be neutrons equals 16. Next one. How does our sun produce energy and make elements? It's the same process. It's the fusion of simple things. The simplest thing is hydrogen into helium releases energy. Helium fuses into bigger. Helium fuses into bigger and bigger stuff. There's a limit. It'll only, in our sun, it'll only go up to iron. But that's not, didn't ask us anything more about that. If it did ask us about, like, what about larger elements, we'd have to talk about larger stars and supernovas. Periodic trends and how atoms combine. Atomic radii. Okay, so this is a two-part question. This is really two questions. They're asking, why does atomic radii decrease moving left to right and increase moving down a group? Let me look at the pictures. Is that true? Yes, they definitely get bigger going down. They definitely get smaller going across. How come? Well, let's choose one at a time. Let's pick the down. As we go down, every time we have another energy level, when we're drawing, like, say, potassium's Bohr model, potassium has 19 protons, and we said only 2 electrons can fit in the first energy level. The next energy level puts it out there a ways. So when we add an energy level, it gets bigger, and then the next energy level puts it out there a ways, and that makes it even bigger, and that last one is way out there in another energy level. So first one, as we, let's see, I want to go to the increase. It increases going down due to adding an energy level or shell. Not so when we go left to right. Everything in a row or a period, everything that goes across has the same exact number of energy levels. So why did they get smaller? Well, it's not because of energy levels. It's because of more protons pull in the electrons closer. So chlorine with 17 protons, that's a lot of gravity, pulls its 3 energy levels in tight, whereas sodium also has 3 energy levels, but those 11 protons can't pull in those energy levels as tightly. 3 energy levels, but they're not held as tight. There's not as much Coulombic attraction. So how do I word that? It decreases moving left to right because more protons pull electrons in tighter, more Coulombic attraction. Next thing is about ionization energy. And once again, this is a two-part question. They want to know about the 2 different trends. Why does ionization energy decrease as we go down? Not increase, but decrease. And increase as we go across. First off, we got to make sure we understand what ionization energy is. It's not the energy to take every electron away. It's just that energy needed right now. We usually put the word first in there, to take that first electron away. So we don't have to figure out how many it needs to lose or anything. It's just how easy is it to take it. And it really does have to do with the same thing we were just discussing, atomic radii. Let's see, why does it increase moving left to right? Since electrons are closer to nucleus, because it's a smaller radii, they are held tighter. I likened it to a daycare. There's lots of eyes keeping all the little ones close. Not so when we move, it decreases moving down as atomic radius increases. It takes, let's see, they are held less tight by the nucleus. The outermost valence, but just all the electrons are held less tight by nucleus. Face below, men in the well diagrams. Magnesium and sulfur, draw the pictures next to one another. I'm going to need magnesium, and I'm going to need sulfur. I need the top to be here. Magnesium, I need to make it 12 protons deep, because magnesium is number 12. I need to put 12 men in there. 2 go on the bottom, or the first energy level. I'm going to do this times 8. And see this, I'm going to put these right up near the top. I know magnesium's really, really reactive. And it's pretty darn easy for those 2 guys that are out there to get out and go somewhere else. Sulfur's different. Sulfur's number 16. That means if I make the tops the same, I have to make this deeper. It is 16 protons deep. I'm going to put 2 on the bottom, just like I did. I'm going to put a shelf that has times 8. Now I need 6 more on a shelf. Check out, I'm gonna, for the analogy, I'm making these not close to the top. And I'm going to try to draw 1, 2, 3, 4, 5, 6 people there. So this is my diagram. The next thing says explain which element has the highest first ionization energy. So if we were using the analogy of there's a party and a full party is 8, the reality is this, none of these sulfur ones want to leave. They say, wouldn't it be better if 2 people came to join us? And these 2 do want to leave because they want to go join a party of 8 because they're not going to find 6 people to climb in and join them. So why is it harder? Let's see, which one has the highest first ionization energy? Since these ones aren't leaving, sulfur has higher ionization energy. But we just discussed that, and that has to do with its radius. I'm going to look just to say, if I'm using the analogy, they are further from top of well. Okay, next question. Using Bohr's models, Lewis models, or a men in the well model? Okay, which model do I use? I don't like Lewis model as much for ionics. I think it works better for covalent or molecular bonding. The men in the well certainly could work, but I already did that, and it's up there, and it says I have to draw a model. So if I did do this, I would say that the analogy would be, here's a party of 6. They're not quite happy. Here's a party of 2. These 2 people would move over to that party. That would leave the magnesium with a +2 charge and leave the sulfur with a -2 charge. Why? 2 more electrons than protons. Why? 2 less electrons than protons. You know what I'm going to do though? I'm going to go with my favorite, the Bohr's model. Magnesium with 12 protons, 2 in the first, 8 in the second, 2 in the third. If it's near sulfur with 16 protons, also 2 in the first, also 8 in the second, but also 6 in the third, I'm going to say like these 2 go over here and make 8. So this loses 2, gain 2. When it loses 2, this is magnesium. Now it has a +2 charge. This is sulfur. It now has a -2 charge. A match made. Now they stick together because of opposite charges. This says to explain it. I just explain it in words, and I have a diagram. You'd need to put a little bit more explanation to get the full points for that. And I'm just going to tell you I don't like this SO2. I don't think that the bonding that we did, the Lewis structures that we did, really, it doesn't really do it justice because you have to know that there's a 1 double, so I'm just skipping number SO2. Maybe I'll put on a CO2 and a CCl4, a carbon tetrachloride. How would I go about doing Lewis structures for CO2 or CCl4? I know it wasn't on there, but SO2 will not be on the exam. CO2, while I'm looking at this must be the central atom, so I'm going to put a C in the middle. I like to start and just put how many electrons does it have. These are valence electrons. These valence electrons get situated around the outside, and each side has to have 1 before it can ever have 2. We have 4 places for things to bond. Oxygen can't bond in all 4 of them. There's only 2 of them, so I'll put 1 on each side. Oxygen brings 6 to the table. 1, 2, 3, 4, 5, 6. Doesn't matter really where I put them. but I do know that I need to have this one making a bond. And I'm going to have 1, 2, 3, 4, 5, 6. And that also makes a bond. So the big question is the carbon happy? Does the carbon have its full number? Well, it does not. There's only 1, 2, 3, 4, 5, 6 around carbon. So this and this one are going to share. Carbon says, hey, oxygen, you have a lone one, and I have a lone one. Actually, carbon looks over here and it sees another lone one. So when I draw this, it'll be C with an O, C with an O. But I have to make sure I still represent all these electrons. So I'll put 2 there, 2 there, 2 there, and 2 there. CO2 has 2 double bonds. Carbon tetrachloride wasn't on there. I'll still start with carbon and put 1, 2, 3, 4. Things only bond where there's singles, but all of them have singles, so I can put chlorine, 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 chlorine. In this case, I'd have to include all of the extra dots. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, because chlorine has 7. There's a very much slightly different way I could write it, but I don't have to. This would suffice. But instead of these 2 dots there, I could show that as a line that represents 2 electrons, represents 2, represents 2, represents 2. I don't care either way. Both of them are a correct Lewis structure.